Okay. So I just want to talk a little bit about solvable groups. Okay. So we have our definition. Okay. So let's start with a normal series. Like this. So we have, what does this mean? So I have a group G, and then G1 is a normal subgroup of G. G2 is a normal subgroup of G1. Okay. And we call this a normal series. Okay. Okay. This normal series is called Abelian. If G0 mod G1, G1 mod G2, so on, are all Abelian. And 2, it's called cyclic. Well, you can probably guess if all the quotients are cyclic. Okay. Okay, let's do a quick example. Okay. Let A be an abelian group. Okay. An abelian normal series where A is the identity next. The reason is, well, A mod the trivial group is an abelian group, right? What is my reasoning? Well, I just have to check that A mod the trivial group is abelian, but A mod the trivial group is just isomorphic to A. Okay, and what is a cyclic series? Well, it depends on what A is. Well, if A is cyclic, then that is a cyclic series is itself. So let's do like a particular example. Let's do Z mod 2Z cross Z mod 6Z cross Z mod 30Z. Okay. Okay, so this is a group. The elements of the group have like 3 coordinates, and the first coordinate lives in the integer, and the third coordinate lives in the integers mod 30. Okay, so what's my cyclic series going to be? Well, so I call this A. So we start with A. And then, so we have an abelian group, and all the subgroups of an abelian group are subgroups such what when I take the quotient, I get a cyclic group. So my first group I'll take will be Z mod 2Z cross Z mod 6Z cross. So for this, I want the trivial subgroup of Z mod 30Z. So we could call that we could call that 30Z mod 30Z, or we could just call it cross 0. Yeah, let's do that. Okay, and now before I move on, I want to explain to you why is A mod by this subgroup a cyclic group. Well, to explain that, I want to, this is where we use isomorphism theorems. So let's explain why this mod this is cyclic. So you define phi from A to Z mod 30Z by the rule that phi of ABC equals C. Remember, A is a Cartesian product of three things: Z mod 2Z, that's where little a comes from; Z mod 6Z, that's where B comes from; and Z mod 30Z, that's where C comes from. Okay. So we notice phi is a homomorphism. Phi is onto. Let me just write down what a homomorphism means for these groups. It just means like phi of ABC plus phi of A prime, B prime, C prime equals phi of A plus A prime, B plus B prime, C plus C prime. That's what a homomorphism means. It's because the groups that I'm talking about, we usually define them using addition. Okay. Now, if I look at both sides of this equation, on the left-hand side, we have phi of ABC is just C, phi of A prime, B prime, C prime is just C prime. So we have C plus C prime, and phi of this is also C plus C prime. These are both equal, so we have a homomorphism. Also, it is clearly onto, because C can take any value in Z mod 30Z, and so it's automatically onto just by our construction. Okay, so it's an onto homomorphism. We want to know what is the kernel, and we have phi of ABC equals 0 if and only if, so 0, that's the identity of Z mod 30Z, and this equals 0 if and only if, well, C equals 0. Okay, so the kernel of phi, that is the set of all ABCs in A satisfying C equals 0. In other words, it's the set of all AB zeros in A. Okay. Well, A is Z mod 2Z cross Z mod 6Z. So A can be in Z mod 2Z, B can be in Z mod 6Z, and 0 is just 0. That's just one thing. Okay, so this is just what we wrote. Okay, so now the kernel is this. So first isomorphism theorem tells us that A mod the kernel of phi is isomorphic to phi of A. What is phi of A? Well, phi is onto, so this is just Z mod 30Z. Okay, and what's kernel of phi? Well, kernel of phi was the subgroup we wrote down above. We just shift it down a little bit. We proved this is the kernel of phi. Okay, so now we know for sure that A mod, Z mod 2Z cross Z mod 6Z cross 0 is isomorphic to Z mod 30Z, a cyclic group. Okay, so now this is our first part of a cyclic series. So we have A, then we have Z mod 2Z cross Z mod 6Z cross 0, and then normal inside that, which giving a cyclic quotient. Well, we just try the same thing again. Z mod 2Z cross 0 cross 0, and then contained in that we just have 0 0 0. So now we have a sequence of subgroups, and each quotient like 1 by the next is a cyclic group. So this is a cyclic series. Okay. So that is just what can happen for abelian groups. I guess, I mean, for non-abelian groups, of course, it might get more complicated. Okay, and the last thing I want to talk to you about today is actually just nothing. Let's just leave it till Friday. There's no point in rushing it, I guess. Okay, so let's leave it there. Okay, so yeah, just one final thing. Please look out for assignment 5 and a few videos under the tutorial playlist for this class. Okay. Anyways, thank you everyone for watching. Yep. Okay.